Hello students, welcome back. We completed sections 1 and 2. But before starting section 3, let's have a brief recap. Back in section 1, we defined the cyclic group and went through some examples of it. And then we stated and proved a major theorem like this. Theorem 1.5. A subgroup of a cyclic group is cyclic. Pretty much everything in lesson 4 revolves around this. For instance, here's an immediate corollary, which says every subgroup of Z is of the same form, MZ. Basically, the set of all multiples of a certain integer M. Consequently, it successfully characterized all subgroups of Z under the addition. And then we went to the greatest common divisor, and this is actually the number theory version. Here, we did a little bit differently using abstract algebra language by setting up a certain set through linear combination like this, and we proved that this is a subgroup. Now Z is cyclic, so this subgroup is also cyclic. It has to have a generator, and if you have a negative generator, put negative on it to make it positive. Consequently, we can always find a non-negative generator, which we call the greatest common divisor, because we can prove that that non-negative generator is a common divisor like this, and also the greatest common divisor like that. This one also proves the uniqueness. So we have a well-defined, unique greatest common divisor, and we use that for example, like this, Euclid lemma as an application, and here's another application, LCM, etc. Okay, that was a quick review. Now let's go to some properties of cyclic groups. And in section 3, we're going to study infinite cyclic groups, and in section 4, finite cyclic groups. Infinite cyclic groups are easier because eventually everything is the same as Z. Everything is isomorphic to Z under the addition. They're all the same, basically. However, this is a grand conclusion. We have to prove it. In the end, it becomes really simple, but unless you prove it, it's not that simple. So we have to take steps. Let's begin. Here's the first step. Each power expression is unique. What do you mean by that? Start from an infinite cyclic group, G, generated by A. Then each expression, a to the n power, is unique. All a to the n powers are all distinct, basically. Here's a symbolic expression. If G is cyclic and has infinite order, and a to the h power and k power are the same, then the powers h and k minus must be the same. Here I said a to the h power is equal to a to the k power if and only if h and k are the same, but you don't really have to worry too much about if and only if. One direction is trivial. If h and k are the same, then of course these two are the same. It's the other direction that we have to work out. Okay, how do we prove that? First, we're going to set up a proof by contradiction. Suppose that the conclusion is false. That is, we have a distinct pair of integers, h and k, so that the powers are the same. So, h to the h power and h to the k power are the same, but h and k are different. Without loss of generality, we can assume h is greater. If the other way around, we can just rename it. And consequently, h minus k is strictly positive. So what am I going to do here? That's what I'm up to, h to the k power. These are the same. And then multiply the same thing to both left-hand side and right-hand side. So h to the a minus k power is equal to e. And here, please make this observation. That's greater than 0, but everything is integer here. All these powers are integer powers. So actually, you can say that this belongs to z plus. Okay, so that belongs to z plus, the set of positive integers, and a to that power belongs to e. Is highlighted in purple and brown respectively. Does it help? Well, we'll see. Let's go to step 2. How do we utilize the conclusion of step 1 here? Well, that's the same computation. And then we define M as the minimum of this set, which comes from the set of all positive integers with this property. A to that power is e. And then look at this. By the setup, such positive integer exists, h minus k. So this set here is non-empty. So there is well-defined minimum. Remember, z plus is well-ordered. So every non-empty subset has the minimum. And we established that this is non-empty. We found out something. So M is the minimum. Then M satisfies this property. So a to the m power, oops. Let's do this again. A to the m power is equal to e. And m is in between like that. Sorry, I'm making a lot of typos while speaking and writing at the same time. You see, m must belong here, so we have to have this. And then m is the minimum, so it should be less than or equal. And then m belongs to z plus, so it should be greater than 0. You see, you can get all kind of thing out of there. By the way, haven't we seen this before? Does it ring a bell? Yes, you have. In the proof of theorem 1.5, we went through this. Remember, when you're looking for a generator, a to the m power, m is actually the minimum of the set, which comes from the set of positive integers with this property, this one here. Let me copy and paste this somewhere around here. And then compare. If H is a trivial group, E, then everything is exactly the same. So basically, we are talking about the same idea. The same idea repeated here again. And please recall that we used the very same idea with the division algorithm and all. Okay, that was step 2. And how does it help? Well, we're going to claim that G is actually this. a squared, a to the third power all the way over to m minus 1, and that's it. Clearly, everything here belongs to G. Yes, that's true, because a belongs to G, so any power belongs to G. But then again, there's no more because G is cyclic. So arbitrary element of G must be of this form. Let's see, let me rewrite like this. Something belongs to G if and only if yeah, let's rewrite like this. So everything is of this form. And then e to m minus 1. And then mth power is back to e. n plus 1 power back to 1, n plus 2 power back to 2, and then another round, 2m, 3m, 4m, we're going to cover everything positive. And if you go backward, everything negative as well. So yes, this is actually equal to g. You can use that kind of naive argument and do some induction. But a little bit better way to do that is to use the division algorithm as a matter of fact. You see, arbitrary element is of form a to the m power, so apply the division algorithm. Divide n by m. Can we do that? Yes, because m is strictly greater than 0. So yes, it's a positive integer, so we can divide by m. So what do we have? The dividend is quotient times divisor plus the remainder. And the remainder is greater than or equal to 0, but strictly less than the divisor. And then the same computation we did before. A to the nth power is basically qm plus r power, and then divide qm power times r power. Qm power is actually a to the m power to the q power, and then what is a to the m power? That's e. So e to the q power, which is e, yeah, we have a to the r power. So everything boils down to a to the r power, and r is always between 0 and m, so these will cover everything. Consequence, we have the equality, so G is actually a finite set. We have a finite group, but that's a contradiction because we started from an infinite group. As a matter of fact, we can rigorously prove that this G has order precisely m because there's no duplicate among this either. You can actually prove it, but that's not what we are up to here. We got a contradiction and that's sufficient for us. And as for the more careful consideration of that, well, we'll answer that question in section 4 of this notebook when we deal with finite cyclic groups. So what did you get? Each power expression is unique. And let's go to the next step. All non-trivial subgroups are infinite. Please recall all subgroups are cyclic. And then if you have trivial subgroup, then of course it has only one element, but anything non-trivial will have a to the m power, appropriate m power. And remember, how did you get a to the m power? Remember that? That's how we got it. And then basically the idea is this: a to the m power to the another k power, whatever it is, you're going to get a to the mk power, and these are all unique. These are all distinct if you have different k values. Therefore, we have to have infinitely many different values. You can set up a little bit more formal approach and prove it like this if you want to, but the main idea is already there. The detail is left to the students. So, what did you get? All power expressions are all distinct, and all non-trivial subgroups are infinite. And finally, they're all isomorphic to Z. In other words, essentially the same. How do you prove that? We just define a certain map from G to Z, like this, a to the n power going to n, and we can actually prove that this actually proves the group operation, and phi is actually 1 to n onto. How do you do that? Well, that's left as a homework problem. This one is going to be pretty simple, straightforward, and this one needs a bit of a thinking, but actually this is straightforward as well. Alright, so much for section 3.